Awesome. So I guess it's day two for the data science conference. I'm definitely super excited to see you guys here. And so today, this is probably the first workshop for today, which is making pseudo data with GANs. But before I jump into the presentation, I would just like to know a little bit about the audience. How many of us has joined in the presentation so far? And yeah, so first of all, hi, good morning, everyone. The reason why you cannot see me is because my camera is suddenly stopped working. It was working perfectly yesterday, and then it has suddenly decided not to work. I'm sorry, but just last moment things. But I can assure you, I don't look like the emoji in the chat. Awesome. So before we move ahead into the presentation, can we know a little bit about you guys? How many of us here are actually students who want to learn about data science, machine learning, and deep learning? Give me a thumbs up if you guys are students. I see not many students here. How many of us are working professionals who are actually working in the data science industry as maybe data scientists, data analysts, machine learning engineers, or something else? Oh, I see. Hi, Mahesh. Who else working in the data industry? Hi, Sean. Okay. And how many of us are here? I see. Lifelong student professional. We all are lifelong students. I see. And how many of us are really not related to data science but are still working in the tech field? Thumbs up for tech. Just tech, not really related to data science. Oh, we have a student. Perfect. Okay, so today's presentation is going to be a little math heavy. Hi, John, lifelong data analyst. Great. Tech field, Jyotsna. Okay, perfect. All right, so actually today's presentation is going to be a little math heavy, but I will try to make it as simple as possible. So I've packed a lot of information for you guys. I've at the end of the presentation, I'll share the link with you so that you can go on to the presentation later and review whatever we have discussed in this maybe 50 minutes or so. And then I have also packed a small task for you, or maybe a notebook which you can run, and we can see how we can generate pseudo data with GANs. So first of all, since we have a variety of different people here, students, tech professionals, data science people, what are GANs? If anybody knows, just give me a thumbs up or a comment in the chat if you know what are GANs, which is generative adversarial networks. It's actually great that this workshop is the first thing in the morning. Otherwise, it would have been very heavy for you guys. Trust me. So anyone who has any idea what GANs are? Cool. So GANs are actually kind of an AI which help in generating data or maybe generating artificial data, right? So in data science, machine learning, artificial intelligence, we need data to solve a particular problem, right? And that's the biggest challenge that in industry we in a lot of use cases we don't get enough data. We don't have enough data to train our machine learning models or data science algorithms on. So GAN is one way using which we can generate artificial or fake data, which we call as pseudo data. So we can generate images, we can generate text, we can generate audio, and we can generate anything that you can think of. Till date, there have been only very basic type of machine learning models, like maybe classification or regression. But until recently, GANs was developed by Goodfellow, which is who is a very famous data scientist from Apple. Hi, Danish. So, and now what GANs do is they generate the data. They are not just limited to maybe supervised or unsupervised tasks, but these are kind of a different algorithms, I would say. Although they are supervised, but they are rather more complex than that. Before we move ahead into the presentation, do you have any examples in your mind that AI has solved over the years? Can you give me any examples of AI or machine learning that you see around yourself? Alexa is one example, which understands our speech. Any other examples like Alexa around yourself? There are so many self-driving cars. Another example of AI, Facebook feed. Yeah, so Facebook feed customizes itself, predict machine failures. Absolutely. Recommendation engines. Definitely. Recommendation for movies that Netflix uses. Forecasting power. Yeah. So yeah, these are all examples and applications of machine learning AI. Anomaly detection. Absolutely. And all Snapchat filters are, yeah, you can say that. They're a kind of machine learning AI models. Okay, so these are actually all the things that we have discussed so far in the charts. These are rather very vanilla or classic machine learning problems. But now GANs are kind of complicated because they don't essentially solve a problem, but they generate artificial data. So without delaying it further, let's start with the outline for today. So we are going to introduce GANs, which we already have. We are going to learn the challenges which we face while training GANs and some of the applications of GANs, because I think uh, maybe it will be very difficult for us to really train GANs, but if we know the application, how useful they are, maybe it'll help us or maybe it'll incline us towards learning more about GANs. All right, so the motivation, the architecture, the objectives. So, generative adversarial networks. Generative is when we learn a generative model, which means it is a model that generates the data which is similar to the training data. So generative is when it generates a data which is similar to the input training data. It could be images, it could be text, it could be audio, it could be songs, it could be anything else. It totally depends upon what kind of input that you are giving into the model, right? Then we have adversarial. Adversarial is trained in adversarial setting, which means trained in a different setting, which means that the generator is trained in a different setting, and that's why it tries to create or maybe duplicate the input training data in a different kind of setting. And then networks, because it uses deep neural networks, right? Okay. Why generative model? We have only seen the discriminative model so far, which I was talking about. All the examples that you see in the chat, like anomaly detection, forecasting power, recommendation, Facebook feed, all these are examples of discriminative models. We have given an image or an input and we predict the label. Estimation of probability of y given the input x. This is discriminative model which describe the data, what kind of data we have input. If we have input, let's say a cat, it will tell us that this is a cat. If we have input a dog, it will tell us that this is a dog. So it describes the data, right? So we have only seen discriminative models so far in general AI world until GAN's came. Discriminative models have several key limitations. They can't model probability of X, that is probability of seeing a certain image, which means let's say we have hundreds of samples data, and in that sample data we have, let's say, dog, we have cats, we have different kind of dogs, we have different kind of cats. So discriminative models cannot really determine the probability of whether that the input data, what is the probability that will be a dog or a cat, because they are not designed that way, thus can't sample from px and can't generate new images. Generative models in general cope with all of the above. They can model probability of X, and also they can generate the new images. So this is the magic of GANs. This is the actual input image, and they give you an output, an image like this, which is very similar to the input image. So this is the ground truth, which is the actual input image, and this is the adversarial image. Throughout the presentation, if you have any questions, just put it down in the chat, and I'll make sure that I answer those questions. Now, which one do you think is a computer generated image? Is it the first one or the second one? Put it in the chat. Which one do you think is a computer generated image? The first one or the second one? Okay, nice. Okay. And you see, so the thing is, it is confusing. We really cannot say if the first one is computer generated or the second one is computer generated. And that's how real GAN's result are. So actually the answer is the second one. The details, if you focus on the details, you'll see that there are more details. Not easy to take, yeah. So if you see that in the first one there are more details, like for example this, and in the water, and otherwise as well in other small things, the number of details are more in the second image, while other is the first one is more chaos, you would say. So because there are certain details here, this is this one is the real image and this was the computer image, generated image. These are some more applications of GANs, which is uh, a recent machine learning architecture by NVIDIA. You input this, and the model will give you this as output, which is called as nature GAN. You build this on a piece of paper in the computer, like on maybe Microsoft Paint. You create this, you save that as an image, and you feed that into the model, and this is what you will get from the model output, which is really fascinating. If you just give this as input, this is what you will get. So you will just have to indicate what you want, and it will essentially create that landscape for you. And this model is just for landscapes. Okay. Coming to GAN's architecture, how GANs essentially work. So there is a generator and there is a discriminator. So what happens is that we feed real. So a very good question from Danish, which is, can we do this stuff using encoder decoder model? So yeah, the answer is yes. We can do this using variational autoencoders, but there are certain challenges there as well, and no doubt there are certain challenges here as well. But GANs are rather more efficient and more accurate than GAN than autoencoders. Sorry. All right. So understanding the on a very high level view the architecture, this is the generator. This entire cell or block, you can say, this block is generator, and this block is differentiator. What happens is that we have real world images here, we sample it, and we import it to the discriminator. And this discriminator discriminates between real and fake images. Here we have a latent random variable which is basically generating fake images. Okay, so generator is generating fake images, real images are here. Samples from both of them are coming into the discriminator, and the discriminator kind of classifies whether the coming image is real or fake and gives us a particular loss based on the difference from the actual data. So this model kind of improves itself until the sample produced by the generator is as good as the real world images. And when the generated samples are as good as the real world images, we reach a loss which is very less. So the overall idea is to generate images which are very close or very similar to the real world images so that we achieve the minimum loss. Or you can also say it the other way around, that the discriminator tries to minimize the loss and it tries to understand at a position wherever we achieve images which are very similar to real world and we have reached a position wherein the error is very small. Does that make sense? Any questions on how this is working? Think of it as like um, we have a real person here and we have an AI here, right? And this is kind of a validator. Okay. So the real person is sending the data, the validator is validating, the AI is also sending some fake images, and the validator is validating. But since the training is going on and the model is training, at every iteration, at every process, this random latent variable is improving the quality of images that it is generating. And over time, it makes better and better quality images, and it reaches a point wherein the images generated by the generator are as good as real world images. And at that point of time, the loss is minimum, the loss is least, because both the images are very similar to each other. And that is when we say that the model has been trained. How does it relate to Turing test? So um, okay, so the thing is, Turing test is for chatbots to understand whether or how intelligent a particular chatbot is, to understand whether a particular chatbot has reached human intelligence or it can fool humans. And this is really not chatbot. So this is every AI has different application. This one has different application. The Turing test was specifically designed for AI who can respond or communicate. So there is a slight contextual difference here. The next question is, what loss function is most appropriate for this task to use in discriminator? So it totally depends upon different use cases, what kind of data we are generating, right? Different types of GANs have different losses. There is not one loss that would be appropriate here. Can the random variable also consist of real images? So actually, latent random variable is, you can say, it generates initially when the model starts training, it just generates noise. So actually, it has nothing to do with real images. It artificially creates all the data. In the starting, it is just black and white noise. And over time, when the modeling happens, it improves the quality of its images or the data that it's preparing. If the quality of real data is not good, I think that's a very important question. That if the quality of the training data is only not good, we won't be able to get results as we were expecting. So since the training data is only not good, the latent random variable will generate images which are also not good. So eventually it won't be of any benefit to us. So the first thing is the data should be of high quality. And there is a very famous saying in data science, which is garbage in, garbage out, which means if you give garbage to the model, you will get garbage out of the model. Okay, so the first and the foremost thing is that always deal with good quality data. Okay, interesting, right? How this entire thing works in a way. And the funny part is that the founder, the person who invented this, actually thought of this idea when he was at a bar. Can you start with generator with a starting image instead of a black and white noise? Then it's not like that. Generator is something which starts with random values, and random values are always black white noise. So we don't tell it that we are generating an image or we are generating a text data or we are generating something else. It automatically tries to mimic the real world images. So it does not know what it is trying to build. It starts with random noise and then tries to mimic the actual original training data. Think of it as like a person who knows nothing about the real world, only ones and zeros. So it is just randomly giving any zeros and ones, and then over time it is learning and then improving its quality of results or predictions or the data that it is producing. Yeah. Training the discriminator. So back propagation happens. So I really don't want to go into the details how neural networks work, but I think I've explained how it usually happens. So the real world samples are like this, and in the starting the generator creates samples like this, which is just black and white noise. And then back propagation happens, the weights are changed, and over time it produces good values. Generator in action. So what we essentially, so here is a little math, and what we call it is as the min max problem. So GANs have this problem which is known as the min max problem. We are trying to minimize the maximum gain that the generator can have. So the generator is trying to maximize its reward. Sorry, the discriminator is trying to maximize its reward, which means how much can it differentiate the actual from the fake data. So it's trying to maximize that, while the generator is trying to minimize the discriminator's reward. So what is generator doing? It's trying to minimize what the discriminator is trying to maximize, because the duty of the discriminator is to discriminate, and the generator's duty is the exactly opposite, that it does not want the discriminator to discriminate, right? So generator wants to fool the discriminator, while the discriminator wants to validate very effectively. So these are like opposite roles in how they work. And that's why this is a min max problem. The discriminator is trying to maximize while the generator is trying to minimize. So this is one of the challenges in when we train GANs, which is we usually don't find a value which satisfies or which gives good results, because this min max problem is not easy to solve. I'll, I can maybe give you another intuitive example. So you must be in scenarios in life wherein when you try to solve one problem in your life, another problem occurs, and when you go try that problem in your life, the earlier problem comes back, right? It's like you are trying to solve different problems in your life, and when you work on one, the other one comes up, and when you work on the other one, the earlier one comes up. So it's the same scenario here, wherein when we are trying to maximize the discriminator's gain, but the generator is also trying to minimize it. So the model is always kind of in this confusion of what to do. And if it reaches a sweet spot where it is able to solve this problem, we get awesome results. Otherwise, we usually end up with just black and white noise. On a very intuitive level, this is right. Okay, these are just algorithmic view how the discriminator updates its samples and the generator updates its weights. So this is the generated samples from black and white images. If we are giving real world images in GANs, this is the output that we get. Although these faces are not very similar to the real world images, but still they are in the process of becoming good ones. So this is the output that we get from. So this is the output that we will get from discriminator or the generator. Question for everyone. These faces as output will we get from the generator or the discriminator? Yeah. What do you think? Okay. So yeah, I think I am able to convey the point. Exactly. So these images will be generated from the generator. So if I may go back, what happens is once the model is trained, we detach this part. Okay, we detach this part and then use it to generate the samples. Yeah. This is CFR dataset, which is a very famous dataset which has different images. I'm sure things might not be clear here, but these are images of animals. And this is in the process of creating the final results, but this is just in between the training. So from black and white noise, this is in the process of creating images of animals. This is a later stage of generating bedroom images. DC GAN is deep convolution GAN. It is one of the types of GAN that we've used, and you can see that it has created very realistic bedroom images. Isn't this amazing how GANs are working in creating these images, right? Deep convolution GANs, this is the general architecture where they use the convolution neural networks as the general architecture inside the generators, and then they use discriminators which are batch normalized. So we were talking about latent vectors capturing interesting patterns. This is one pattern that you can also build, which is if you train the images with this, which is man with the glasses, man without glasses, and then woman without glasses, you can also create samples of women with glasses. So that means we train specific GANs for specific requirements. So can a particular GAN generate for both dogs and cats? Not really, but it can create different kind of dogs. Within the dog species, it can create different kind of dogs. And maybe we can have a GAN in the future which can create different kind of dogs as well as cats. Because this is a research field, I cannot really say no to anything because maybe in the future we might have a model which can. So this is how we can create fake samples by combining different samples, man with glasses, without, and women without, and we can then actually have women with the glasses. Do you see why there is a minus and why there is a plus here? So in this man, if we subtract the person, we will just get the glasses, right? If we subtract the man, we will just get the glasses. And then on these glasses, if we plus the women, we will get women with glasses. Yeah. So now coming to advantages, challenges, and the applications. Advantage of GANs is that sampling is straightforward, which is we don't really need to use state-of-the-art techniques. We can just pick the training data and use them for the training. Then training does not involve maximum likelihood estimation. It is robust to overfitting since generator never sees the training data. So when, as I mentioned, that the generator never sees the training data, so it never overfits. So all these terms are very specific to data science, machine learning people. So I'll rather be very general here. I'll rather not try to dig, dive into the details, right? And I think someone asked me whether we can do this with autoencoders. So we can do this with Boltzmann machines, deep belief networks, as well as variational autoencoders. Yeah. Now, there are certain problems with GANs. One is non-convergence, which I already told you, which is it is difficult to find the correct spot for the solution of the min-max problem. And then there is model collapse. Model collapse is when it is not able to imitate the input data. What is the sample size is good enough? So Alexi, actually, we need pretty big size to get good results. Although we can get good results with just maybe 100 or 200 images, but if we need great results, we really need a good bunch of samples. But a basic GAN can be built with just maybe somewhere around 100, 150 images. Yeah. All right. So training problems. We have non-convergence and we have model collapse. So the usual deep learning models that we have in the industry, they try to maximize the reward or minimize its loss, which is they try to minimize the error. Generally, all the models that there are, they try to minimize the loss, right? And what happens is that we use stochastic gradient descent to find the optimal parameters. SGD has a convergence guarantees under certain conditions, and it is really the perfect recipe to achieving great results in regular deep learning models. But when we talk about GANs, GANs have a different kind of problem. GANs, the discriminator is trying to maximize its reward, and the generator is trying to minimize the discriminator's reward, which is like opposite to what each other, right? So the generator is trying to minimize the discriminator's reward, and discriminator is trying to maximize its reward. And this algorithm, which is used in all the deep learning models for training, is not really designed to find the perfect answer to this min-max solution. And that's why usually we hit a blocker or we face some challenges when we are trying to build a solution for this. So one of the challenges is that it's not very easy to train again because of not having the correct algorithms for solving a min-max algorithm. So this is a little explanation around what really happens. As I was telling you that when you try to solve one part of your life, the other mess comes up, and when you solve the other mess, the earlier mess comes up. So this is the same problem wherein when you try to optimize or make better predictions for X, your Y will deteriorate, and when you try to make good predictions or improve the value of Y, your X deteriorates, and then eventually you'll end up at the same place where you begin with. So You will try different solutions, you'll try optimizing X, you'll try optimizing Y, but eventually you'll arrive at the same state after doing a lot of iterations, because the min max problem is like that, right? I hope this makes sense to everyone. Give me a thumbs up if we are not g- going haywire here. Any questions so far? Okay, so now the model collapse. This is the model collapse wherein this is the expected output, but this is the actual output, which means that the output, or maybe the generator, is not able to produce as much quality images as required. So it is not able to perform perfectly or as it is required by the model. And this steps is basically the number of iterations. In 5,000 training, the actual result should be this, but it is still here, and so on and so forth. So these are some of the real examples of the problems faced. This was the actual data, and this is what we end up with. Very close, but still they are maybe not as good. And this is also because some, I think one of you asked that what if the training data is not good? So this is one such example wherein the training data was not good, and that's why we could not get the good or appreciative results. Now we have a lot of applications for GANs. I have to skip a couple of slides because I really need you guys to try and build your own first GAN. So I've also prepared a notebook that you can run. So I'll just wrap up the presentation, then we will try to actually build a tram, because that's what gives us the real kick. So we can have a lot of these bedrooms. We can also generate images of celebs, which are, so all these are totally fictional celebrities. And then we can also have 3D faces, which means we can generate faces at different angles. So at different lightings, at different wide or narrow face broadness, and at different elevations, which is at different elevations of the face and at different angles. So we can, for the same face, we can generate different angles. So you give the front face to the computer, and it will give you how you look from the side, how you look from the top, how you look from the bottom. This is, all these can be done with GANs. Similarly, for 3D objects, for chairs, for cars, and in fact, these have been currently been using in a lot of industries around the world, in the automotive industry with cars, in the furniture industry with furniture, that you just upload one photo of the furniture, and it will give you a 3D image from every angle that is there. Right. Then we have the InfoGAN, which is another example or another application of GAN, and it gives us different kind of results. So coming to conditional GANs, we will actually be working on this data set. We will have an input data, which will have 0, 1s, and 2 images of 0, 1, 2, 3, which is called the MNSIT data set. And we will create a GAN which will create artificial data of 0 to 9 digits. So we will have input data which will have images of different digits, and we will train a GAN that will give us similar images from 0 to 9 to different objects. Yeah, should we start? Give me a thumbs up if you guys are ready. Waiting for your thumbs ups so that we can right away jump on to training the model. Okay, here we are then. You'll find a link here, open that link, and it'll take you here. Training DC GAN using Google Colab TPU. So I'll give you 2 to 3 minutes to open the notebook, set this up, and connect this. This is called a notebook. Okay, you can't access. 1 minute. I'll make it public. My bad. Okay, now you can access. Now you can access this. Yeah. Hope everyone can access this now. Once you are here, all you need to do is okay, perfect. Thanks for letting me know, Alexa. So once you are here, all you need to do is just run these cells. Run this, then the next one. It will install different libraries, different dependencies for you. Run this, then come to the next cell. Each of these are known as cells. Okay, so run this. It will work fine for you. It might give me some problems, but it will work fine for you. I've run the first 2 cells by clicking here. It will say successfully installed. Ignore this error if you're facing this. Let me know once you have completed the first 2, 3 steps. Can't see what I'm clicking on. Can you see this arrow? You have to click on this to run this. Click on this, then click on the next one. Here. Is it clear now? Awesome. So just waiting for all of you to complete the first 2 steps, run the first 2 cells, and for others, go on and run all the cells that there are. This one, which is now we will import the libraries, then run all the other cells below this also. Collab TPU. Okay, so what you can do is go to Edit, Notebook Setting, and in here, select TPU. Yeah, make sense? Once you select this, you won't get this error. How many of us have reached here, imported the libraries? Give me a thumbs up in the charts. Once you have reached here, just keep on running all these cells. You can press Shift Enter as well. Shift plus Enter. Where is everyone? Facing any troubles, any issues? Okay, perfect. Okay, great. So keep running these cells by clicking here or just pressing Shift plus Enter in your keyboard. I think my screen is clear to everyone. Akshara, there might be some problems at your end. So keep running all the cells that are here. Here we have a discriminative model, and in the next cell we have a generative model. Initializing weight, and this is use of detach. You remember we talked about, okay, Darren. So all you need to do is just run these cells by clicking the arrow here. From the starting of the notebook, just continue running all the cells one by one, and you'll be able to replicate whatever we are doing. Yeah. Let me know if you have any troubles, Darren. So we talked a little about detach method, which means that when the model is trained, we detach the generator from the entire architecture and then use just the generator. Thanks for letting us know, Hina. Running this and now starting this process. The final last cell. How many of are here at the last cell? Let's quickly run all the cells and come to the last cell. Okay, perfect. Let's run all the cells. Let me know if you have any troubles. Awesome.
Hi, Hasan. Could you reshare your screen, please?
I guess my screen has stopped. Let me reshare. Um, Going good on Epoch 7. Great.
Okay. Are you able to reshare, Hassan, your screen?
No, I'm still finding the option.
It should be just at your, I'll make this full screen, the toolbar immediately above floating. You
Got it.
can see the share icon there. Thank you.
Okay, my screen is back. Or, yes. Okay, how many of us are here at Epoch 7? Epoch 8. So, this process is actually training, right? We are training our model. These epochs are actually the iterations that are happening, the first iteration, the second. With every iteration, our model is improving. It started from black and white noise, and then it is improving with every iteration, right? And once it is completed, we'll see the results and see how, what quality images did it give us. Oh wow, epoch 14. I'm sure some of us might be having some troubles. Let me know, guys. While it is training, I hope my screen is visible. I'd like to show some more applications of GANs. So we can also convert a black and white image to a color image. We can convert a drawing into an actual bag. We can convert a day image into the night image. We can convert a satellite image into a map image. So many applications of GANs. These are image to image translations. So a lot of things that we can do. And we can do text to image synthesis. So there is a, I'll write the name here. Try that out. For dull E. So this is an AI. You write the name and it will generate images with that name. For example, if you write uh, mountains, sunset in the mountains, so it will generate image of a sunset in the mountains. Whatever you write, it will generate images of that for you, and that is known as text to image synthesis. You write the text, it will convert that text into image. For example, here, if you write, I want a white flower with green background, it will give you this. So these are also applications of GAN, which is converting text into image. Then this is explaining the architecture. We also can do face aging. We just need to have a training data of a person who is young and the same person when that person is aged. So when we have that, we can actually train a model which will be able to generate an image of you, how you look when you turn old. And if you remember, there was a filter, I think Snapchat filter, which showed us the aged image of ours. That was actually a GAN model. So we can also build face aging models with GANs. So this is phase aging with conditional GANs. Original, this is the initial recurve section, pixelize, and then phase aging over the years. Coupled GANs. Coupled GANs are basically an example of what we were discussing, wherein we couple different features of different images and generate a new image. For example, we have different hair colors, we have different facial expressions, and we have different sunglasses. So we create images which have different hair colors, facial expressions from these, and sunglasses from here. Coming to the summary, the generator tries to generate the samples, and discriminator tries to distinguish the samples from the generator and the real data distribution. Both networks are trained adversarially to fool the other component. So each network trains to fool the other component. And in this process, both models become better at their respective tasks. Why use GANs? For the purpose of this workshop, we can use GAN for generating pseudo data. There are a lot of different examples and learning material here. And before we come to the questions, I would also like to share this with you. I'm sharing the link. And now when we come back to the notebook, I've shared the link to the presentation in the chat so that you can revert back to this presentation. This is the samples generated for me. It might be different for you. The actual data was something like this, MNSIT dataset. This was the actual data, very well-defined images. But here that we see, some of the images are not clear. For example, what is this? This is not one, this is not two, this is, I don't know what. Similarly, what is this? So although it has done a good job at generating images, this is a clear 8, clear 3, 9, I don't know what this is. So these are although some of the samples, and a lot of them are actually clear that yes, these are clear images. But then there are some samples which we don't have any idea what those are. So this was the end of the workshop, generating pseudo data with GANs. Let me know if you have any questions. I've already shared the notebook and the presentation with you. Please feel free to ask me questions offline as well, maybe on LinkedIn or otherwise. I'll be happy to help. Great, awesome. Good to see that. Okay, thank you everyone for joining in today. And I think I had a very great time doing this for you. Awesome. I'll see you guys maybe next time. All the best. Cheers. Bye bye.